All right, today we are going to be continuing our discussion on sequences in series by talking about a type of proof called mathematical induction. All right, so mathematical induction, as I just said, is a form of mathematical proof. It is not one of those two-column proofs that you did in geometry, but it is a type of mathematical proof. When is it used? It's typically used when you have some sort of pattern or formula that seems to work for several values of n. Now, the problem with something like this is if you see a pattern, it may or may not be the case that that pattern is going to continue to hold as you continue for values of n as they get higher and higher. So since we're not going to be able to show that for all values of n it's going to work, right? Because typically that means that you may need to show it from n all the way to infinity. We can use this type of proof in order to show that this pattern or this formula will continue to work by this method of proof, mathematical induction. Okay, so let's talk about how this mathematical induction works. So the principle of mathematical induction. So we're going to let a capital P with sub n be a statement that involves the positive integer n. Okay, so if we say P3 is true, then that is saying that this is true for when n equals 3. Okay, so how this induction works is there are two parts to it. The first part is if P1 is true, so if it's true for n equals 1 for the first term in the sequence, and you know that the truth of P sub k implies the truth of P sub k plus 1 for every positive k. Okay, so this is where we're actually going to use k. Okay, so we're going to say no matter what k is, we can show that P sub k plus 1, the one right after it, is also going to hold true. Okay, so if you can show that the first statement is true, and you can show that no matter where you're on the sequence, you can prove that the following statement in the sequence will also hold true for any positive value of k, then you will have shown that P sub n must be true for all positive integers n. So kind of a way to maybe visualize what all this is saying is what we have here. So say you want to show that P sub n is true for all n. So you want to show that some pattern, some sequence, some formula is going to hold true as n goes to infinity. So this is what we want to show. We want to show this is true for P1, P2, P3, all the way up to K plus 3, and continuing on and on and on. So in order to show that these are all true, right, we're not sure but whether or not this is true. This is kind of our guess. So what we need to do is we need to show that the first statement is true. So think of this as a row of dominoes that I have here. We have to show that the first statement is true. Okay. Well, that's great and all, and we can find that the second statement is true, the third statement is true, but we'd have to continue on and on. So what mathematical induction says is we need to show that no matter where we are in the sequence, so for example, let's say we're at P sub k, we want to show that if P sub k is true, it implies that P sub k plus 1 is also going to be true. So in other words, what you're trying to show is if one domino is true somewhere in there, doesn't matter where, it will make the one right after it fall. Now, if you can show that the first statement is true, and you can show that any domino will topple over the domino after it, then what ends up happening? Well, if you can show both of those, then you know that P sub n is true for all n, because, well, then P1 is true, and if P1 is true, and we know that no matter where you're in the sequence, if something is true, it will topple over the next one, then P2 must be true. Well, if P2 is true, and we know that PK implies PK plus 1, then P3 must also be true, and so on and so on. So that's how those two steps will actually help you prove that it's true for all values of n. Okay, so let's do some examples so we can see how we actually go about these two steps. So here's the first example. Use mathematical induction to show the following. Now, if you were to come up with what the sum of all the terms are from 1 all the way up to n, and you were to do it for the first term, then the first two terms, and the first three terms, what ends up happening, what you end up finding, is that the sum of the first n terms with using this formula 2n minus 1 is always going to be n squared. Okay, so what this is saying is for the first term, the sum of the first term is just going to be 1. Some of the first two terms in the sequence will be 4. Some of the first three terms in the sequence will be 9, and so on. Now, you can obviously keep going and say, okay, when n equals 4, does it also equal n squared? When n equals 5, does it also equal n squared? But you can't do that for infinity, right? But it seems, at least at this point it seems, that it looks like it's always going to equal n squared. But we have to be able to prove it without having to show it true for every single value of n. So we're going to use mathematical induction. So the first step is to show that it is true for P1. Okay. So we're going to show P1 is true. So we're going to plug in 1 for n. So the sum of the first one term is equal to, well, 2 times 1 minus 1 is the only term in the sequence. And 2 minus 1 is equal to 1. And if you were looking on the right-hand side now, we plugged in n equals 1. So 1 squared is also equal to 1. So that holds true. Okay, so we've successfully done the first step, which is to show that P1 is true. So you take the left-hand side, simplify it down. Take the right-hand side, simplify it down. And you should have the same thing. That's the first step. All right, the second step is the harder step. We need to show that if P sub k is true, then P sub k plus 1 is true. So we're going to start by writing out P sub k. We're going to deal with P sub k plus 1 in a second, but we're going to just focus on P sub k. So instead of writing n in there, we're going to write k, because we're somewhere in the sequence, doesn't matter where, but we're going to say we're at k. Okay, so if P sub k is true, so we're going to say, okay, P sub k is true. We're going to write out what that is on the left-hand side, and it will seem like it doesn't really make a lot of sense just yet, but it's going to help us show that P sub k plus 1 will be true, so long as P sub k is true. Okay, so on the left-hand side of this equation, if we were to write this out, we would say, okay, this is 2 times 1 minus 1 plus 2 times 2 minus 1 plus 2 times 3 minus 1 plus and so on until you get all the way up to k. So this goes all the way up to 2 times k minus 1, which is equal to k squared. Okay, let's simplify this left-hand side as much as we can. So 2 times 1 minus 1, that's 1. 2 times 2 minus 1, that's 3. 2 times 3 minus 1, that's 5, and so on. So we have 1 plus 3 plus 5 all the way up to 2k minus 1, and that's equal to k squared. Okay, so that's all you're doing up to this point. We haven't used P sub k plus 1 yet, but we're going to use this statement, which is P sub k. So P sub k being true means that this formula that we just wrote down is true. Okay, so you can think of this as part B of step 2. Now we're going to write out for P sub k plus 1. So instead of being from 1 to k, it's from 1 all the way to k plus 1. And what do we want to show? We want to show that this is equal to k plus 1 in parentheses squared, right? We're replacing n with k plus 1. So right now we don't know if this statement right here is true, right? We said P sub k is true, so if p sub k is true, we have to show that, therefore, p sub k plus 1 must also be true. So we're not going to do anything with the right-hand side. We're just going to work with the left-hand side. So let's write out the left-hand side just like we did with p sub k. So we would start with 2 times 1 minus 1 plus 2 times 2 minus 1. And then this goes up to what? 2 times k minus 1, 2 times k plus 1 minus 1. Now you'll notice something here. We saw this section right here for p sub k, right? That was what p sub k gave us on the left-hand side. And on the right-hand side, we know this is equal to k squared. So we can replace what's in the blue parentheses there with k squared. And that helps simplify p sub k plus 1 for us. Okay, so the blue parentheses there is equal to k squared from the last slide. And now we'll write down everything else. So this is plus 2k plus 2, distribute that, minus 1. Again, we are trying to show that it's in fact equal to the right-hand side, so we're not doing anything with the right-hand side right now. Let's simplify this left-hand side even more. Let's see, that comes out to be k squared plus 2k plus 1. And then this is actually factorable, right? We can actually write this as what? K plus 1 times k plus 1, or k plus 1 squared, which is in fact what we have on the right-hand side. Right, so we have successfully shown that this left-hand side of p sub k plus 1 is going to equal k plus 1 squared because we know p sub k is true, right? Without that substitution that we did with the blue parentheses there, we wouldn't be able to simplify this down. So, because you have been able to show that p sub 1 is true, and you've shown that p sub k implies that p sub k plus 1 is going to be true, therefore you've shown that this pattern is always going to work for all values of n. All right, we're going to do another example. So this one looks a little bit more complicated, but the same steps will apply. Okay, so step 1, show that p sub 1 is true. So, in other words, we're going to plug in 1 for n and show that the left-hand side gives us the same thing as if we were to plug in 1 for n on the right-hand side. All right, so this is equal to 1. And on the right-hand side, we have 1 times 1 plus 1 times 2 times 1 plus 1, which ends up being 6 divided by 6, which is equal to 1. So it looks like p sub 1 is true, right? The left-hand side gives you 1, the right-hand side gives you 1. All right. So now let's go on to step 2. We can think of it as part A of step 2. So we need to show p sub k is true, implies that p sub k plus 1 is true. Start with the first part. We're going to write out what p sub k being true gives us in terms of an equation. So again, instead of writing n, we're going to plug in k. Now you're going to do it to both sides because we're saying if it's true. So p sub k is true, and then we'll use that for p sub k plus 1. Okay, so plugging in k for where you see n. Now on the left-hand side, this means we have, what, 1 squared plus 2 squared plus 3 squared all the way up to k squared. And that's equal to k times k plus 1 times 2k plus 1 all over 6. That's the equation that we're going to use to help us with the substitution for p sub k plus 1. Now, algebraically, you might imagine this is going to look like a little bit more work. It's absolutely doable, but it is a little bit more work than the first example. So now we have to show that p sub k plus 1 is going to be true, which means we need to know what we need to get on the right-hand side. So plugging in k plus 1 in for n this time. Okay, now on the right-hand side, that gives us what? K plus 1, k plus 2, and then if you were to plug in k plus 1 in for n in that last part, and then do some distribution and simplifying, you get 2k plus 3, and put that all over 6. Okay, so now let's write out what we have on the left-hand side. Now remember, we're not doing anything with the right-hand side. We just know that that's what we need to show that the left-hand side is equal to. Okay, that's after we take the left-hand side and simplify it as much as we can, we need to get that for the right-hand side. So we have 1 squared plus 2 squared all the way up to k squared, and then up to k plus 1 squared. We're going to do something similar where we're going to do a sort of substitution. So the 1 squared all the way up to k squared, we know what that's equal to because we know p sub k is true. So we take that and we write out that's equal to what? K times k plus 1 times 2k plus 1 all over 6. And then put in the plus k plus 1 squared. And now we need to somehow simplify this, what we have right here, so that it looks like that right-hand side. Okay, let's start off by at least getting it into one fraction, because we know the right-hand side is just one fraction. So we'll put that second term there over 6 as well, so it'll be 6 times k plus 1 squared over 6. Okay, so we'll add those two together now that we have the same denominator. So now we just have one fraction. And now there are a couple ways to go about this. You could try and multiply everything out, but note that that right-hand side, everything's factored in the numerator. So that's going to be a lot of factoring if we have to multiply everything out first. So let's see if there's more that we can do in terms of factoring. So if you take a look at the numerator, we actually have a k plus 1 in the first term, and we have two k plus 1s in the second. So we're going to just take one of those k plus 1s out from each term and factor that out. So we have k plus 1. That leaves us with what? K and 2k plus 1 plus 6 times k plus 1. Okay, so we have part of what we need from the right-hand side. Now the rest of this has to factor into that k plus 2, 2k plus 3 thing. Now it looks like we're not going to be able to factor anything else out here, so let's go ahead and multiply what we have left inside those brackets. So that's going to be 2k squared plus k plus 6k plus 6. We'll combine the k and the 6k, so we have 7k. And then that is actually factorable, and that comes out to be k plus 2 and 2k plus 3, which is in fact what we needed on that right-hand side. And so now we've shown that that left-hand side of p sub k plus 1 is equal to the right-hand side of p sub k plus 1. So therefore, since we've shown that this is true for the first one, p1, and we've shown that p sub k implies p sub k plus 1, therefore we know this is going to hold true for all values of n. Alright, so in summary, mathematical induction is useful, particularly in this chapter, as we're talking about sequences and series and we see patterns, and we want to be able to show that certain patterns or certain formulas are going to hold true for these summations. And in order to do that, we can't possibly show that this is going to be true for all values of n, because that goes to infinity. So mathematical induction allows us to use those two steps to show if the first step is true, and we can show that for any step, the following domino will be knocked over as well. Then we know that, well, the first domino is going to knock over the second domino is going to knock over the third one, and then therefore it must be true for all values of n.